First question we're going to answer is, how old is the solar system? And the answer is, it's rather old. Well, it's easy to look at me and see that I'm old, but how do you look at an astronomical system and notice that it's old? Well, it turns out you date the rocks. We find on Earth some rocks that are as old as 4.4 billion years. We abbreviate that gigayears. Such rocks are rare on Earth. Most of the rocks we find on Earth are tens or hundreds of millions of years old. But on the moon, old rocks are far more common, and the oldest moon rocks are as old as 4.5 billion years old. Meteorites, meteors that fall onto Earth, we'll talk about that later on. Space rocks can be as old as a little older than that, 4.54 billion years. We sense a pattern, and indeed our best estimate for the age of the solar system is about 4.56 billion years. So 4.56 billion years ago is when the solar system formed. That's a pretty ambitious statement. How do you know how long ago the solar system formed? The answer, of course, is more physics. And the technology that we use to figure out the age of a rock is called radioactive dating. And to understand how we date rocks, we're going to have to carry our understanding of the structure of the atom deeper in. And we're going to have to look inside the atomic nucleus that Rutherford discovered carries the entire mass of an atom. And remember that a species of atom is identified by its atomic number, the positive charge in the nucleus. And what Rutherford discovers is that that charge is carried basically by a number z of positively charged massive particles we now call protons. He just called them hydrogen nuclei. A proton is nothing other than the nucleus of a hydrogen atom. And so inside the nucleus are z hydrogen nuclei. This is a discovery by Rutherford in 1917. This accounts for approximately half of the mass of an average nucleus. What is the rest? Well, the rest is obviously neutral matter. Chadwick in 1932 discovers the neutron, and it's realized that the rest of the mass of an atomic nucleus, besides the protons, is made up of A minus Z of these neutral particles called neutrons that each have about the same mass as a proton. So helium nucleus, for example, contains 2 protons and 2 neutrons for a total atomic mass of 4. Now, if you look up the atomic mass of helium in a periodic table, you'll discover it's slightly less than 4. The reason for this is that the same combination of protons can appear with differing number of neutrons. Note that since the protons determine the charge of the nucleus, this will lead to 2 atoms which have the same electron cloud and so are chemically indistinguishable but have different mass. In fact, helium, for example, can appear in 2 forms. There are helium nuclei with 2 neutrons and 2 protons for an atomic mass of 4, and there's a less stable isotope, as it is called, of helium, helium-3, with 2 protons, so the same electron structure as helium, but only 1 neutron. And so Z determines the chemistry, the number A minus Z of neutrons determines the mass, and in general you can combine neutrons and protons in various combinations. This all brings up a great question, of course. Once you realize that the atomic nucleus is not all in one piece, it's made up of neutral and positive particles, you can ask, why doesn't the thing blow up? There is a whole lot of positive charge. There are these repellent Coulomb interactions between the protons. What is it that holds the nucleus together? We'll get to that later, but at the moment, it suggests, and you are right, that most combinations of neutrons and protons do not like to stay together, and most assemblies you could put together decay, and in fact many of those that we find in nature do decay, and they decay, it is discovered in the late 19th, early 20th century, in one of 3 ways. One is a process called alpha decay. This is the emission of what is called an alpha particle and is soon discovered to be nothing other than a helium nucleus, a nucleus of the stable isotope of helium with 2 protons and 2 neutrons. And so many nuclei decay by emitting, notice, they emit a helium nucleus. This means the remaining nucleus has a different nuclear charge, so you've achieved chemical transmutation. One element is transmuted into another. The object of alchemy is achieved. Sadly, lead is more often the product than the initial part of this, and turning lead to gold is not yet a commercial enterprise. The other species of decay, continuing the order, is beta decay. The beta rays that nuclei emit are discovered to be nothing other than electrons, and a nucleus can emit an electron. I said that electric charge is conserved, and indeed, the emission of an electron is found to be associated with a conversion of a neutron to a proton. So in a sense, a neutron decays into a proton and an electron. The proton remains in the nucleus. The electron escapes. The net result is that the total number of nucleons in the nucleus is unchanged, A is unchanged, but Z increases by 1. So again, we've changed the elements. There is also positive beta decay, in which the particle emitted has the same mass as the electron, but positive charge as opposed to the electron's negative charge. And this is accompanied by the conversion of a proton to a neutron. So again, A is unchanged in beta decay, but in this kind of beta decay, Z, in fact, decreases by 1. Many heavy elements also spontaneously undergo fission, which is a more dramatic thing where a heavy nucleus basically splits up into two smaller nuclei, often throwing off a couple of alpha particles as well. And this is a process in which, again, you start with a heavy nucleus and end with two smaller ones, and all of these are in general accompanied by the emission of high-energy photons, gamma rays. So these processes go on. What has all that got to do with dating the solar system? Well, we'll see that in a minute. And radioactivity, however, has lots of applications, and it contributes much to our life. Let's start with something we know. Remember, helium, we said, was a rare element on Earth. It was first discovered on the sun. If you did your homework last week, you might understand what's going on. At the temperatures in the Earth, so helium is lighter than air. Helium, if we pop a helium balloon, then the helium without the balloon will float in the Earth's atmosphere up to the top, to the outer atmosphere, to something called the exosphere. And at the temperatures of about 1,000 or 1,500 degree Kelvin that obtain there, the kinetic energy of a helium atom with its small mass means that its velocity is about a sixth, if you computed last week, of the escape velocity at that altitude. That means the hotter, faster, remember there's a statistical distribution, this is only an average kinetic energy, the faster helium atoms evaporate and escape Earth. And so in fact, Earth does not have the mass needed to retain an atmosphere of helium. This explains why, despite the fact that hydrogen and helium are the most common species of atoms in the solar system, our atmosphere is not comprised of hydrogen and helium. Hydrogen and helium, hydrogen molecules with an atomic mass of 2, and helium atoms with an atomic mass of 4 move fast enough to escape the Earth's gravity. We still have lots of hydrogen on Earth because hydrogen binds and is found in things like water. Helium, being a noble gas, does not bind to anything, so any atom of helium will eventually evaporate. In fact, Earth loses large quantities of helium to space all the time. So where, you ask, do we find helium to fill our helium balloons? Earth, having been around, I claim, for 4 billion years, would have been completely free of helium were it not for the fact that helium is being produced inside the Earth and escaping out to the atmosphere at a constant rate. And helium is being produced as alpha decay, so every bit of helium, every atom of helium you've ever put in a birthday balloon is the result of radioactive decay inside the Earth. Primordial helium is long gone. In addition, this process, both the helium nuclei, the alpha particles, the beta particles, the gamma rays, escape from the nucleus with lots of energy. They plow into the surrounding medium and distribute this energy. What this ends up doing is dumping energy in the surroundings. This is bad if the surroundings are your lungs, but in the inside of the Earth, this turns out to be a source of internal heat. So there is, at the inside the Earth, an ongoing process of radioactive decay. We'll see it's mostly happening in the core and mantle, and this heats the inside of the Earth. That's something that radioactivity can do. But for our purposes, what we want to understand is how we use radioactivity to date a rock. So the idea is that radioactive decay is a random process. Any given atom is independently, or any given nucleus will decay independently with a probability per unit time that is constant. What this amounts to is that if you have a sample within some prescribed time, dependent on the species of nucleus that you are studying, half of all the atoms will have decayed. And then within that same period, half of the remaining atoms will have decayed. The process has no memory, once a nucleus has not decayed for some time, the clock starts over. It's as likely to decay in the next second as it was in the previous second, given that it didn't decay. This leads to a mathematical expression for the time dependence of the number of nuclei of a given species, which says that in a given time, called the half-life, t1 half, a half of the sample will have decayed. So if you start with some number at time 0, when t is equal to t half, the half-life, you will have half of the sample left. Another half-life later, you will have a quarter, and so on exponentially. And what that means is, on the other hand, this decay, say if the predominant mode of decay is alpha decay, then you have one nucleus that when it decays will produce another species of nucleus. So with time, the concentration of what is called the daughter nucleus will increase while the parent concentration decreases. Now, if you knew the initial concentrations of daughter and parent, if you could, and for some reason, know what you started with, then you could compare the initial concentration to the current concentration and extract from that the amount of time that has passed. The best way to do this in dating rocks, though there are other forms, carbon dating, where you make a different comparison, but imagine that you have a process where the daughter nucleus is a chemical element, remember these are different chemical elements, whose chemistry is such that it escapes, it boils out of liquid rock, and therefore is not contained within a freshly solidified rock. So when a piece of rock solidifies, there are no daughter nuclei, but the parent nucleus is trapped, is bound, can be bound within the crystal. Then, once the rock is solid, the parent nuclei start to decay, and they produce concentrations of the daughter. The ratio of concentrations is then dependent on time like this. If you can measure both of these, you can, and you know the half-life, then you can extract the length of time that has passed. Can we find such candidates? Surely. The beautiful thing is that the degree of instability of various nuclear species varies wildly from fractions of a second to billions of years for the half-life. In particular, many of the isotopes of uranium decay. They decay via various processes, but the end product of many of the processes is lead, and it turns out that a mineral called zircon binds uranium when it forms, but not lead. So when a zircon rock forms, it will contain essentially no lead. But it might contain trace amounts of uranium. That uranium will decay with half-lives of the order of a few billion years. And so if you find lead in a chunk of zircon, it was produced there by radioactivity. If you compare the concentration of lead to the concentration of uranium, you can figure out how long that rock has been sitting there. This is tricky because lead can in fact escape. Lead is not completely trapped, and so you might find less lead than should be there. In the case of lead and uranium, we're fortunate there are two different isotopes of uranium, produce two different isotopes of lead as their final product, and with slightly different half-lives. And so you can compare the relative concentration of the two isotopes of lead and the two isotopes of uranium. And in this beautiful diagram, you see sort of the plots by age of the predicted ratios of concentrations. You see that the samples have lost some lead. Their lead concentration is lower than the uranium concentration you would predict, but they lie along this line, and the intersection of the two lines gives you the age of these rocks. And this is the way that we date the solar system. This is how we know that the oldest rocks we find in the solar system are 4.5 billion years old.